Gaussian processes are a hugely powerful tool for regression, not to mention the fact that they occupy a very special place in the theory of probability. And besides all that, they're really fun to play with, and they're beautiful actually to visualize. So maybe I'll mention just a few applications of Gaussian processes. Perhaps the most widely the area in which they're most widely used is what's called geostatistics, which is roughly speaking modeling spatial aspects of the world on sort of a large scale, and things like geology and oceanography and meteorology and so on. And yet another application, very different, of Gaussian processes is to things which are evolving over time. Like for example, if you want to track an object over time, where it's going, like an airplane, you want to track. And yet another completely different application is to finance. Gaussian processes are very often used in finance and physics, and I mean there's just a litany of applications: physics, diffusion processes, and all this stuff. Okay, so that's applications, and let's start out. What is this beast? What is this mysterious Gaussian process? Well, we can start right off the bat with the definition. So for any set S, a Gaussian process, or process you might say, depending on where you're from, which we'll often abbreviate GP, a Gaussian process on S is a set or a collection set of random variables, which I'll denote in this way. Maybe I'll use Z because I want to use X for something else. So it's a bunch of random variables ZT that are indexed by these elements T, which are in the set S. I'll put these parentheses rather than a set, but I could have put a set braces here. And it's a set of random variables like this, such that they have the following property. For any, maybe I'll put it down here, for any n, and for any t1 up to tn, so there's going to be n t's in S, the vector zt1 up to z, that's a big comma, ztn, that vector, is a Gaussian. It's Gaussian distributed. It's a multivariate. Whenever we say a vector is Gaussian, we of course mean it's multivariate Gaussian. So that is the definition of a Gaussian process. And this part here, well, these finite dimensional distributions, for each subset, each finite subset of indices t1 through tn, the distribution on that finite set of random variables is what's called the finite dimensional distributions. Those sets of distributions are called the finite dimensional distributions. That's just a little terminology for you. So if you're not familiar with multivariate Gaussians, you are going to need to watch or somehow learn about multivariate Gaussians. Otherwise, the rest of this section is going to be hopeless. So let's first look at a couple very simple examples. So the first example is actually going to be a trivial example, but it's to make this seem a little less mysterious to you. So the first example is we can take S to just be some integers 1 through d, and then we can take this collection of random variables, which I'll often abbreviate this by just this open paren, just zt in parens, rather than write this all out. This is then just the vector z1 up to zd, a vector in Rd, a random vector. And if we put some Gaussian distribution on this, some multivariate Gaussian distribution, then of course any subset of those random variables is going to be multivariate Gaussian. That follows by the affine property of Gaussian distributions. And so this satisfies this definition, right? Because it's It's a collection of random variables on this set S, and for any subset of those random variables, that subset is Gaussian distributed. So this is actually, I mean, if you know what a multivariate Gaussian is, then this is the first example of a Gaussian process that you can sort of just very easily get your head wrapped around. But in some sense, this is too trivial. This is not really, doesn't really capture the full flavor of what's going on here. So here's a little less trivial. This may be the simplest possible Gaussian process that is non-trivial. So this one will be random lines. Random lines. This was just a multivariate Gaussian. So for this example, second example, we'll take S to be the real number. So we're going to have an uncountable collection of random variables here. So now things are starting to get interesting. And we'll take ZT, we'll define ZT to be T times W, where W is a random variable that is, let's say it's just a normal random variable with zero mean and unit variance. So it's just a standard normal random variable. So this is just in R. Now before we verify the definition, maybe just I'll draw the picture of what this is doing. Let's draw. Whoa, that's a terrible drawing. Draw the picture here. So if we draw a value, of W, let's put Z. So ZT is going to be on this axis, and this is going to be T here. So if we draw a value of W, let's say we draw maybe we get like 0.2 or something. So I'm going to draw the value of W on this vertical line here that I'm indicating. So maybe 0.2 is right around there. And then what is ZT? Well, ZT is just T times W. So if W was 0.2, then when T is 1, then ZT is going to be 0.2. And when T is 1/2, then ZT is going to be 0.1, and so on, and it's just going to follow along this line right here, this straight line. And when T is 0, of course, ZT will be 0, and so on. So it's just the straight line that goes through 0 and that point. If we drew another, if W on some other, if we sampled W again and we got a different value, maybe we got that, whatever that is, then ZT, this collection of random variables, is going to look like this. So maybe let me just pause for a second here to say what I'm drawing. At each value T, like here, for example, this is like minus 1/2, there is a random variable, Z minus 1/2. This value here is Z minus 1/2. The value that this takes here is a random variable, and it's the one that's in this collection with the index minus 1/2. And likewise, for any other T, there is some random variable. Okay, so now if we were to draw a bunch of other values of W, so maybe we got that one, then we would get the line that goes through 0 and that point, and maybe if we had a whole bunch of others, they're going to be normally distributed, so they're going to look something like this maybe. Normally distributed, because W is a standard normal. And so we're going to get all these lines. Oh, they all have to go through the origin. Something like this. So if we were to draw successive samples of ZT of this Gaussian process, they would look like this. They would just be these random lines. And let's verify that this is, in fact, a Gaussian process. So what do we have to check. We have to check that these vectors, zt1 up to ztn, are always multivariate Gaussian. So let's let t1 through tn be some real numbers. That's what our set S is. And then we have to verify that this vector is multivariate Gaussian. Let's write it this way. Well, what is this? This is just t1. I'll put it over here. This is just t1 times w down to tn w. And we can just factor out the w here. If we think of w as being, well, it is a constant, but we can also think of it as being a 1 by 1 matrix, and we can think of this as being a n by 1 matrix. And since w, this is sort of, we can apply the affine transformation property of multivariate multivariate Gaussian random variables in a sort of very peculiar way, because we're going to think of this as a 1 by 1 multivariate multivariate Gaussian. And so we multiply by a matrix, and we know by the affine property that that is also multivariate normal. So A, this is our AE matrix here. And therefore, this is multivariate normal, or Gaussian, multivariate Gaussian. So this is indeed, and that holds, of course, for any t1 through tn. So this is indeed a Gaussian process. Okay, so those were just some super simple examples, and soon we're going to take a look at some much more interesting examples of Gaussian processes.